Greetings, everyone. Welcome back into college algebra. Time to take a little sidestep for a moment, and we're going to review the topics that were on this first section of algebra topics. Typically, this is where I would put my first test in a traditional college algebra course. So what I'll be doing is working through some previous tests that I've given in the years past. The topics that we will be covering are solving equations mostly, and then solving some inequalities. And of course, all of the different types that we've been talking about up until the point of this video. Quadratic equations, radical equations. And don't forget, radical equations also means fraction exponent equations. Rational equations, which can also mean negative exponent equations. Quadratic types, which are the ones that have the quadratic form, but they don't necessarily have to be something with a squared. They can have the same pattern of a quadratic though. And then of course the othering factoring types that come up with either cubics or with sorting things by groups and other such. Then of course there's absolute value equations. The inequalities, the ones that we typically focus on at this point, are the absolute value, the polynomial, and the rational inequalities, and being able to give those answers in interval notations. Okay, so the way you should probably approach this video is you may want to see the problems, pause me, and see if you can work them out. At this point, we are treating this as a review of all of the topics up to this point. I strongly urge you not to memorize these problems, but to focus on the methods that are going to be employed and practice other problems that are similar to these. Math is learned through practice, not memorization. For the first set of problems here, what I want to focus on is mostly quadratic and polynomial types, and then we'll be branching outward from there into those other types of equations. So as you can see, the first two are definitely quadratic, right? Because you're going to have an x squared as the first in each term. And then you can see this one's similar to a quadratic, but technically it's not full quadratic because it is a negative 2 exponent. However, this does make it a quadratic, quote-unquote, type of equation. But with the negative powers, it's technically a rational equation. And then this last one here is more of a polynomial equation, being that it is to the third power, is a cubic equation, but it employs some of the factoring techniques that we also employ sometimes with quadratics. So let's begin. I have 7x squared minus x equals 2. From this point right here, I of course always want an equals 0 in my quadratics. So I would subtract the 2 from both sides here. That would result in 7x squared minus x minus 2 is equal to 0, right? All I'm doing is subtraction there. I'm just subtracting 2 from both sides, but I don't have like terms on the left-hand side there. Okay, from here, I can see that I'm in standard quadratic format, and you might want to play the game. Some people like doing the factoring game if it's quick and easy. But 7 times negative 2 is negative 14, and there are not two numbers that add to negative 1 that also multiply to negative 14. Not whole numbers anyway. So I'll be using the quadratic formula for this particular problem. So then quadratic formula dictates that 7 is going to be my A, negative 1 is going to be my B, and negative 2 will be my C value. So then I have x is equal to negative b, which is negative 1, plus or minus square root b squared, negative 1 squared, minus 4 times a, which is 7, times c, which is negative 2, all over 2 times a, which is 2 times 7 here. All right, so then after this, I just have some simplifying to do. Negative 1 Of course, I'll have x equals 1 plus or minus there. Inside of my square root, I will have 1. And then the double negative here makes it a plus. And then 4 times 7 times 2 is just 8 times 7, which is 56. And then, of course, in my denominator, I've got 2 times 7, which is 14. Next, I'll just add in my radical there. So I have x is equal to 1 plus or minus the square root of 57 all over 14. And then at this point, I'm going to look at the 57. Let's see, 5 plus 7 is 12, so I can get a 3 out of that. But it's 3 times 19. So this radical cannot be simplified anymore. To make it more of a organized answer, I'm going to take the minus here, and I'm just going to write that as a separate solution so that we can tell that we are in fact getting two solutions here. 1 plus the square root of 57 over 14 and 1 minus the square root of 57 over 14. Typically on my test, I usually tell students to give me exact answers, so that's where we are here. If at any point you were to have to, give an approximate, the only other step here would be to now plug it into your calculator and round to the appropriate number of decimal points. Okay, next question. X times x plus 2 equals negative 3. For this question, I need to get it into the standard format quadratic, and I would like it equal to 0. I can't combine anything while these parentheses are in the way. So I begin by distributing the x. I'll have x squared plus 2x is equal to negative 3. And now we're in a similar format as the last question. I want to have the equal 0. So of course I will start by adding 3 to both sides. I don't have any like terms on the left, so then I'll just be writing them together. X squared plus 2x plus 3 is equal to 0. And then at this point you want to try your different methods, right? For factoring, I would need two numbers that multiply to 3, which add to 2, right? Because it's just a 1 in front of the x squared. I can just look at the last two coefficients there. But there aren't whole numbers that do that. 1 times 3 or negative 1 times negative 3 are your only hopes for multiplication here. And neither of those are going to add to 2. So again, I'm falling down on I need to use the quadratic formula. So then I'll have x is equal to negative 2 plus or minus square root 2 squared minus 4 times 1 times 3 all over 2 times 1. So then I have x is equal to negative 2 plus or minus the square root of 4 minus 12 all over 2. 4 minus 12 being negative 8, of course, makes this a completely different type of answer altogether. The square root of negative 8, we need to remember how to handle the simplification of that. Right? So the square root of negative 8 right here. Remember, I'll have the square root of negative 4 times the square root of 2. And then again, the square root of the negative is going to give me an imaginary part. So the square root of negative 4, I'm going to get 2i. And then the square root of 2 portion, I still can't simplify any further. So I'm getting 2i square root of 2 in the place of that square root of negative 8. So then I go ahead and do that replacement. I have x is equal to negative 2 plus or minus 2i square root of 2 all over 2. But since I can reduce both sides, now remember this is important, since I can reduce all three of these, I go ahead and do it. Negative 2 divided by 2, I get negative 1 plus or minus 2i divided by 2, of course, is just I square root of 2. And at this point, everything is completely simplified. So I'm going to go ahead and write out both solutions separately. Instead of plus and minus right here, I'm just going to put comma -1 minus I square root of 2. And it is, of course, important to note that I do have two complex solutions here, right? A complex number being a number that has a real and an imaginary component. Make sure that you have all of your I's in order. Okay, next we have the rational equation, which is also a quadratic type. 5x to the -2 plus 6x to the -1 plus 1 is equal to 0. Now, of course, I could solve this like a rational and do the whole multiplying by the common denominator thing, but I want to focus on the quote-unquote quadratic type of this format so that it fits into what we're doing here. So there are a couple of different methods that you can employ for this problem. I'm going to focus on the quadratic version of it so that we can enhance that feature. So to look at this as a quadratic type, I do a small replacement for a moment. It's a temporary replacement. Let y equal x to the -2. I'm sorry, x to the -1. Woo, almost messed that one up. If I let y equal x to the -1, then what I get after this is 5y squared plus 6y plus 1 is equal to 0, which is a full-on quadratic. And I'm going to try to solve it with factoring. If I multiply the 5 times 1, right here, 5 times 1 gives me 5. And then in that, if I can find two numbers that multiply to 5, which also add to 6, which, that's easy, 1 times 5, right? 1 plus 5 is 6. So therefore, I can do the factoring version here. So let's go through that real quick. Remember, the way I handle this is I go ahead and put both of the parentheses bubbles, and I put a 5y in front of each one, which of course is incorrect at first. But then I take my two values, the +1 and the +5, and then I try to filter out any extra. I notice 5y plus 1 is completely prime, nothing to factor out there. But the 5y plus 5, I can factor out a 5. So do your divisions. 5 divided by 5 is 1, so I'm left with y plus 1, and then I throw away that 5. It's now safe to bring down the equals 0 because this bottom piece is actually equal to this piece, right? Remember, technically this middle step is not equal to the top one. It's an intermediate that I use. Okay, so now let's go back out of our substitution, okay? What happens is I reverse this substitution here, and everywhere I see y, I just use x to the -1. So I have 5x to the -1 plus 1 times x to the -1 plus 1 equals 0. And then I split and solve them. So I have 5x to the -1 plus 1 is equal to 0, or x to the -1 plus 1 is equal to 0. Okay, so then I'll divide this up, pun intended, and I'll start solving. What I'll do is I'll subtract the 1, and then I'll divide by 5. Now the way I'm going to handle this is with exponents. To handle this with exponents, what I do is I raise this to the power that will give me x to the 1. So in this case, that means that I want to raise this side right here to the -1 power, because -1 times -1 is 1. And remember, exponents that work on each other, you're just multiplying. So that means I'm going to employ a -1 exponent to both sides. Employing that -1 exponent will get me where I want to be. So negative 1 to the negative 1 just gives me x to the 1. So I just put x. And raising something to a negative 1 power keeps the numbers, but does the reciprocal. So I end up with negative 5 over 1, but that's just negative 5. So I get that x is negative 5 as one of my solutions. Over here, a very similar ploy. I just subtract to get negative 1. And then, just like on the other side, I am going to raise both pieces to the negative 1 power. But then, all that gives me is x is equal to negative 1. Because remember, the negative 1 power doesn't change the number, it just does the reciprocal. But 1 over 1 is still 1 over 1. And therefore, I get x equals negative 1. Okay? There's only one other consideration that needs to be done here. And that is to remember that x to the negative 1 is actually 1 over x. And the reason why it's good to focus in on that is to remember anything that has a variable in a denominator should be checked for excluded values. In this case, it would be very bad if x were equal to 0. So we say x cannot equal 0. And it's good to check for that because I want to check my solutions. If either one of these had been 0, I would want to exclude that value. But as it turns out, both of them are non-zero. So in this case, both of those solutions are good to go. Okay, the last one, the cubic over here. I'm going to solve this one by factoring. So the first thing to do would be to get it equal to 0. Of course, that means that I'll be subtracting the 4y, and I'll also be subtracting the 18y squared. So that will give me 9y cubed minus 18y squared minus 4y plus 8 is equal to 0. So at this point, I look at it and I notice it's got 4 terms. So then I remember, oh yeah, factoring with 4 terms, you really got to do it by grouping. Hopefully that works. If not, then you have to come back and try something else. So to factor this by grouping, I separate them and determine if they have things in common. This first grouping right here, right, this piece right here, has a 9y squared in common. So if I factor that out, 9 divided by 9 is 1. Y cubed, take away 2 of them, is just y. Negative 18 divided by 9 is negative 2. And I took both of the y squares, so that's good. Always match the middle sign here, so minus. 4 and 8 have a 4 in common. So that's what I'll be dividing. Negative 4 divided by negative 4 is 1, so I'll get just y. 8 divided by negative 4 is negative 2. That's important. I divided by a negative. Double check. Negative 4 times negative 2 does give me 8. So that's still correct. I then notice that y minus 2 is in common. So I pull that out. And it leaves me with 9y squared minus 4 equal to 0. From here, I can further factor because that is a difference of 2 squares. That will give me 3y minus 2 times 3y plus 2 equal to 0. And at this point, I can just split and solve each piece since they're multiplied and equal to 0. So I'll have y minus 2 equals 0, which I can just add 2 to both sides to get y equals 2. Next, I can get 3y minus 2 is equal to 0. So then I can add the 2 and then divide by 3. So I get y is equal to 2/3. And then very similarly in the last one, 3y plus 2 is equal to 0. So therefore I can subtract a 2 from both sides and then divide by 3. So y is negative 2/3. As always, with problems on a test, I urge you to take extra time if you've got it and plug these back in actually to the original equations to check that they are indeed solutions to these equations. Next, let's take a look at radical and fraction exponent types of equations. These are the ones that I've put on tests before here. We have 5x to the 3/4 plus 300 equals negative 20. So then the way I would start this, of course, I only see a single x. As I call it, I just start unwrapping the present by pulling at each piece. I'll begin by subtracting 300. Minus 300 from both sides. Then lands me with a 5x to the 3/4 is equal to negative 320. Of course, then I will divide both sides by 5. So then I'll have x to the 3/4 is equal to a negative 64. And then I could convert this into a radical. I could say that this is the 4th root and the 3rd power, and then undo each piece separately. But remember, the tactic that we have for dealing with exponents is to just raise it to something that turns it into a 1 exponent. In the case of a fraction, I just use the reciprocal exponent. So I will be raising both sides here to the 4/3 power. In doing so, that's going to give me an x to the 1 power. So just x. And then all I need to do is the 3rd root of negative 64 and raise it to the 4th power. So the 3rd root of negative 64. And then I'm going to raise that to the 4th power. Well, the 3rd root of negative 64 is negative 4. Because negative 4 times negative 4 times negative 4 would give me negative 64. And then negative 4 raised to the 4th power. Of course, there being 4 negatives would make it positive, right? So then I'm going to get x is equal to positive, let's see, 16 squared, that should be 256, right? Now, the other thing we need to consider is that this actually was a radical equation. And I don't mean crazy, I mean using radicals. And the original equation had an even powered radical. Those are the ones especially special that need to be checked. So I'm going to have to take this solution, or possible solution I should say, and plug it back into the original equation and see if it works. I'm already a little suspicious because we had something with an even root here equal to a negative number, and it's not actually defined that way. Remember, if you have the radical already in the equation, you have to take the literal sign that was given. So I'm suspicious that this right here was already a violation because I had a positive even powered root equal to a negative number. Okay, but as I said, we're just going to go back in and check it by plugging it in. So I'm going to take the 256 and plug it in. I have 5 times 256 raised to the 3/4 power plus 300 is equal to negative 20. Okay, well right here, I need to do 256 to the 3/4. So that's going to be the 4th root of 256, which is 4 to the 3rd power. 4 to the 3rd power is 64. And then 5 times 64 is 320. And then 320 plus 300 is 620. This is false, because 620 is not equal to negative 20. So therefore, this is not valid. And since this was our only option, and we've now shown that this is not valid, then I have to give a final answer of no solution. Right? This one's not valid. Therefore, no solution. This equation here has no solution. Next, I have a quadratic type with fraction powers. I know it's a quadratic type because this exponent is double of that one, and we've got the trinomial situation going on. So just like we did before, I'll take steps to make it look like a quadratic, and then we'll bounce back in after we've gotten through any solving methods that we do. Okay, so I'll let y equal x to the 2/3, right? The guy in the middle here. And in doing so, I will have y squared minus 13y plus 36 is equal to 0. This one's a pretty straightforward factorization. I can just say y minus 9 times y minus 4 is equal to 0, because negative 9 plus negative 4 is negative 13, and negative 9 times negative 4 is positive 36. So it was a straightforward trinomial factorization, especially since there was just a 1 in front here, so it was a quick factoring. If you wanted to use quadratic formula, you certainly could. You'll get very similar solutions. I'll do this one slightly different than the last time, just so that, to show you that there is some variety in here. I can split it right here instead of waiting. And I'm going to get that y is equal to 9 or y is equal to 4. At this point, I will switch back to the x world. I'll go ahead and divide this up though. I'm getting x to the 2/3 is equal to 9, or x to the 2/3 is equal to 4. Remember, our trick is to, or our method I should say, is to raise both sides to the reciprocal power, just like this. In doing so, I will get x to the 1, which is just x, and I'll have 9 raised to the reciprocal, so that would be 9 to the 3/2 power. Be careful. I'm noticing here that I bring up a even-powered root. That's the square root that I have introduced. We introduced it into the equation. So it technically brings a plus and minus with it. Plus and minus with it. And I can do the same thing over here. I'll get x is equal to plus or minus 4 to the 3/2 power. Which here what I'm going to get is the square root of 9 is 3. And 3 to the 3rd power is 27. So I'm getting plus or minus 27 for those two solutions. And here, the square root of 4 is 2. 2 raised to the 3 power is 8. So I'm getting plus and minus 8 for these two solutions here. Okay? I urge you to go through and check, but all 4 of these, there are 4 solutions here, right? 2 here and 2 here. And all 4 of them do actually work in this equation, right? Check them just like we did the other one to make sure you see what I'm saying. But all 4 of them do actually come out with a 0 equals 0 once you plug them in and come out. Okay, the last one over here is a radical equation. And it's just in radical form, right? We're not dealing with the fraction powers this time. However, I've got several things going on. I've got an extra variable piece, and it's not just a straightforward get the variable by itself directly. This one has a few extra pieces to it. First, I would like to get the most complicated piece by itself if I can. So that's what I do. I have right here the 1 minus the radical. So I'm going to get rid of the 1. I'm going to subtract the 1 from both sides here. That's going to give me negative square root of 5x minus 5 is equal to x minus 1. At this point, I am going to square both sides. Once I square both sides, the radical will of course be gone, and the square will also take care of that negative, because negative times negative of course is positive. So then what I'm left with on the left side is 5x minus 5. On the right hand side, be very careful. X minus 1 squared is not x squared minus 1 squared. It's x minus 1 times x minus 1, which I'll need to multiply out, FOIL fashion if you will. That's going to give me x squared minus 2x plus 1. I am now noticing that I have converted into a quadratic situation. So my next instinct is, oh, if it's quadratic, all of my methods say get it equal to 0. So that's what we're going to do. I'm going to subtract the 5x and add the 5. So minus 5x plus 5. Therefore, I have 0 is equal to x squared. Let me draw a line and separate this out here. Minus 7x and plus 6. Okay, at this point, factoring our formula because it's a quadratic. I'll go ahead and do factoring because this is just a drop, real easy one, right? Two numbers that multiply to 6 that add to negative 7 are going to be negative 1 and negative 6. When I split and solve, notice that I'm going to get x equals 1 and x equals 6, right? Because x minus 1 equals 0, I'll add 1. X minus 6 equals 0, I'll add 6. Just like before with these, you should check. And I'm going to go ahead and do it this time because only one of them is going to work. How did I know that? I've checked it already. That's okay. You should check also. Don't just guess that one of them will work. Sometimes you will have one of these equations where they both work. Sometimes you'll have it where neither of them work. And on most of the occasions, one of them will work. Okay, so let's check both of these. I'm going to plug in x equals 1 into my equation. So let me split this up here. 1 minus square root of 5 times 1 minus 5 equals 1, right? Because that's x. I'll put a 1 in. 5 times 1, of course, is 5. Minus 5 is 0. Square root of 0 is 0. And I get 1 equals 1. On the other side, I have 1 minus square root of 5 times 6 minus 5 is equal to 6. Right? Because I'm plugging in that on both sides. So then I have 1 minus the square root of 30 minus 5 is equal to 6. And 1 minus the square root of 25 is equal to 6. Which tells me 1 minus 5 equals 6, which tells me negative 4 is equal to 6, which is false. Of course, this other one was true. So then we come back to our solutions over here, and the x equals 6 is not valid, right? So I disregard that one. The one right here, x equals 1, is true, so I keep that one. So my actual solution to this equation is not both of them. It is x equals 1. Now let's look at a couple of rational equations. I know they're rational because they have variables in denominators. And of course, the typical method for things of this complexity is to find a common denominator and multiply by it so as to convert the rational into a more simple, I should say a less complicated is probably the best way to say it, a less complicated equation. Because what can result can either be linear or quadratic a lot of times if it's the typical rationals that we run into at this point. So then on first equation here, the first thing I'm going to look at is my denominators, and I'm noticing that this x squared plus x minus 6 is not factored. So I would start by factoring that. Hopefully when you factor it, you get the other two denominators, because if it's not, then you're going to have a much more complicated equation. X plus 3x minus 2, in fact, is the factorization of that equation. So step 1 would be to multiply the common denominator, which is x plus 3 times x minus 2. I would multiply that here. I would multiply it here. And also here. So going through these pieces here, I can comb out and notice that I get some eliminating portions, right? The x plus 3's right here are going to wipe out 2 times 1. So I'm left with 4 times x minus 2 is equal to, here the x minus 2's are going to go away, leaving me with 5 times x plus 3, plus here both pieces will wipe out and the denominator will be completely gone with the multiplication, solely leaving me with the 2x plus 1. Now I have a completely linear equation in this sense. I'm going to distribute. So I have 4x minus 8 is equal to 5x plus 15 plus 2x plus 1. On the right-hand side, I have some like terms to combine. So I have 4x minus 8 is equal to 7x and plus 16. At this point, I will do a couple of addition subtraction steps. So I'm going to add 8 to both sides in order to get rid of the 8. And I am also going to subtract 7x so as to eliminate the 7x on the other side. So now I have separated variables and non-variables for a total of negative 3x and 24. I will divide both sides by negative 3, which will land me an answer of negative 8. Don't forget to go back and check. Of course, the long version of checking, you should check, and for your own sake, go back and make sure that it does actually work as a solution. But as a superficial check, I also noticed that x cannot be 2, which we haven't violated that one. And also x cannot be negative 3. And again, we haven't violated that one either. Those are my denominators, and these are the values that would cause division by 0. It doesn't violate either one of those. And it does, in fact, actually work out when you sub it back in. Okay, next, on this equation right here, I'm going to employ a very similar method, especially for the first step here. I'm going to notice that one of my denominators needs to be factored. In this case, that would be the d squared minus 9, which factors into d plus 3 times d minus 3. And then I will multiply that denominator to all of the pieces. So I have times d plus 3, d minus 3, d plus 3, d minus 3, d plus 3, d d minus 3. And once I do that, I can reduce quite a bit. So the d minus 3's reduce here, leaving me with 6 times d plus 3. Don't forget the minus is attached to the 4 here. So that's minus 4. The d plus 3's reduce, so leaving me with a d minus 3 multiplication. And in the last one, everything is wiping out, leaving me with just the 24. At this point, I distribute so that I can see where I'm at. I have 6 times d squared. I then also have 18d. I have minus 4d. And notice negative 4 times negative 3, I have a plus 12, still equal to 24. I am noticing that this is a quadratic with the d squared there. So I know that I'm going to want to equal 0. So I'm going to kind of do a two-stage step here. I do want to combine like terms, which I will do. But also, at the same time, I recognize that I need an equal 0. So I will also be subtracting 24 from both sides in order to get the equal 0 on the right-hand side there. Okay, so I have 6 times d squared, and then I have plus 14 times d, and now I've got a negative 12 is equal to 0. At this point, I notice that 6, 14, and 12 all have a 2 in common. I'm going to divide everything by 2, which is completely legal. Dividing by 2, as long as I do it on both sides. And 0 divided by 2 is still 0, so it doesn't take away anything that I already had. Dividing everything by 2 just means I'll have 3 times d squared plus 7 times d minus 6 equals 0. Okay. So I choose this time to use the quadratic formula. We've been doing a lot of factoring. This one may very well be factorable, but I'm just going to use the formula. So d is equal to negative 7 plus or minus square root 7 squared minus 4 times 3 times negative 6 all over 2 times 3. Okay, so then that results in negative 7 plus or minus the square root of 49 plus, because of the double negative, get a plus. 12 times 6 is 72. Alrighty. Over 6. So I get that d is equal to negative 7 plus or minus the square root of 121 all over 6. And we can do the square root of 121. So negative 7 plus or minus 11 over 6, which then I can do negative 7 plus 11 over 6 and negative 7 minus 11 over 6. That gives me 4 over 6, which is 2/3. And I get negative 18 over 6, which is negative 3. Now notice I didn't circle negative 3. A little red flag just went off in my head. I'm coming back up here to notice right here in my divisions, in my original equation, d cannot be 3. And right here, d cannot be negative 3. Because of division by 0 in the original equation, d cannot be negative 3. So this negative 3 is not valid. Therefore, on your paper, you should put the solution is d is equal to 2/3 only, not both 2/3 and negative 3. It's time to look at some absolute value equations and inequalities. They're, approach very similarly, so I have them all on one screen here. So an absolute value equation, like the absolute value of x plus 7 is equal to 4, we would solve by splitting the absolute value. Of course, check that your absolute value is isolated, right? Ours is. And therefore, at this point, I would go ahead and split it into its two possibilities to where x plus 7 is either equal to 4 or x plus 7 is equal to negative 4. From here, I would subtract 7 from both sides, and I would get either that x is negative 3 or that if I subtract 7 here, I would get x is equal to negative 11. So I have these two as solutions. And of course, you should check them, right? Negative 3 plus 7 is 4. Absolute value of 4 is 4. Negative 11 plus 7 is negative 4. Absolute value of negative 4 is also 4. So these two are good solutions. Okay, now an inequality. I approach the inequality the exact same way. However, when you apply the alternate solution, the negative, don't forget that negatives reverse inequalities. So therefore, when I split this one, right, notice the absolute value is isolated, so I can go ahead and split it. I get a 4x plus 8 is greater than 11 portion. I also get a 4x plus 8 is less than negative 11. Okay? In this case, I still use the qualifying conjunction or. Okay? Next, I go ahead and solve, right? I subtract 8. So 4x is greater than 3. And then I divide by 4, so x is greater than 3/4. Okay? Or, here I again subtract 8, which would give me negative 19. And then I divide by 4, which is negative 19/4. Since these are inequalities, we actually want to display the answer as both a graph and an interval notation so that we have all three versions. So therefore, if I draw out a number line, like so, I need to locate 3/4 and negative 19/4. Of course, 3/4 is in between 0 and 1. 19/4, if you use some division, you'll notice that it's in between negative 4 and negative 5. Negative 4 would be negative 16/4. Negative 5 would be negative 20/4. Okay, so then I'll put 0 kind of to one side here. Here's 1, 2. Let's see if I gave myself enough room here. I may not have given myself enough room. I did not. Here's negative 4. Here's negative 5. Put the arrow over here. Okay. Now, negative 19/4, of course, is going to be right here between negative 4 and negative 5. And then 3/4 is going to be right here, like so. Both of these inequalities have no equal sign on them. They're strictly greater or strictly lesser. And I have the or, which means I'm going to put both of these together on the same grid. I'm greater than 3/4. Okay, so I'm going to put a parentheses, and I would shade this way. And then I'm less than negative 19/4. So I would put a parentheses here and shade this way. Finally, the interval notation would be this interval, negative infinity to negative 19/4, union, because they're disjoint, with 3/4 to infinity. And to make it highly technical, you could put the x as an element of, and say that this is your solution set, right? Don't forget this is a set of solutions, because all of the numbers in these groupings would actually cause this to be a true statement. Okay, in the last one here, I start out by noticing that my absolute value is not isolated. It's very important that before you split, you isolate the absolute value. So I'm going to subtract the 6 from both sides. Absolute value of 2x plus 5 is therefore less than or equal to 4. Now I split. Okay, so when I do the split, 2x plus 5 is less than or equal to 4. In the case of a less than, we put and then 2x plus 5 would be greater than or equal to negative 4. Here's sort of a cool little side point on this one. Notice the split works just like all of the rest of them, but I have to do the and. And the reason for this is because of the way the absolute value works, being less than something. Remember, absolute value is like measuring a distance. Okay, so if I'm less than something, instead of getting sections that are like wings like this, I'm actually getting a section that's in between. Okay, so here's the other little point to this. I don't actually have to write these separate. In the case of a less than, I can actually make my work a little bit simpler by saying all of this can be summed up with one statement, like this. 2x plus 5, 2x plus 5 is in between the values of negative 4 and 4. And that's another alternative way of writing this. At this point, I can then solve this compound inequality and get the answer that I want all at once. So I subtract 5 from all three locations. That would be here, here, and here. So I get negative 9 on one side, and I get negative 1 on the other side, and 2x is in between the values of negative 9 and negative 1. So of course then I would divide by 2, which would give me negative 9 over 2 on one side and negative 1/2 on the other. So I have this inequality. X is in between the values of negative 9/2 and negative 1/2. I can go straight over to the interval notation. X is an element of the interval, bracket negative 9/2 comma negative 1/2. So this is the other version of the answer there. And of course the graph would be as simple as getting these two numbers on a number line. Negative 9/2 would be negative 4.5, so it would be between negative 4 and negative 5. If I put 0, negative 1, negative 2, negative 3, negative 4, negative 5. This time I gave myself too much space. Let my arrows go this way. Of course, negative 9 over 2 would be exactly in the middle of negative 4 and negative 5. And negative 1 over 2 would be exactly in the middle of negative 1 and 0. There and there. And the graph would just be brackets or solid dots, depending which one you like. And of course I would be shading in between only. And remember, this is still a solution set, right? All of the numbers in this set would make this a true statement if substituted. To finish up this test review, I now want to take a look at the other types of inequalities that have come up on tests at this point. And it has to do with the advanced technique for solving inequalities. When you have nonlinear inequalities, we don't just start moving things around and trying to get x by itself. Remember, what we do is we separate, find breakpoints, and then make sections that are either all true or all false. Okay, so this polynomial one has appeared on my test in the past, and then I also have a rational one that has appeared on tests in the past. To start with the polynomial one, or actually to start with either one of them, we want to have a 0 on one side because that makes the breakpoints easier to find. So I begin by moving things over to the other side here. I'll add x squared. I will keep the 4x, and I'll subtract the 12. Okay? Now for the moment, notice I will have a 0 on the other side. Instead of putting the less than, all I'm going to put is equals right here. Okay, now this is temporary. Okay, I'm still solving the less than, but to find the breakpoints, I'm going to put equals for right now. Well, okay, and this one I can just solve by factoring. X plus 6 times x minus 2 equals 0. And then right here I can say that either x would have to be negative 6 or x would have to be positive 2. Because I'd have x plus 6 equals 0, that's this, and x minus 2 equals 0. Okay, so what I've done here is just a little bit of side work to find the breaking points where this inequality would sort of balance out or zero out. All right, so negative 6 and positive 2. If you look at those on a number line, right, if I have an x-axis number line here, and let's say zeros here, right, 1, 2, and negative 1, negative 2, negative 3, negative 4, negative 5. As usual, I didn't give myself enough space. I'll spread this out a little bit more. Here's right here, negative 6, and negative 7. Okay, so remember what I'm doing here is I'm splitting this into sections. Okay, so I split it on these breaking points at negative 6 and 2. Okay, so these right here are not actually solutions to the inequality, and that's because there actually is no equals, but I solved the equals to get the breaking points, right? So I have a section over here, which is the interval from negative infinity, comma, negative 6, right? That's this interval. And then I also have the interval from negative 6 to 2. That's this interval. And then I have the interval from 2 to infinity, right? That's this interval. I'm going to test each one of these intervals and see. Okay? Now, what do I mean by test? I mean I'm going to take a number from this section, because everything in each individual section is going to all give the same type of solution, either a yes or a no. And what I do is I just check it in the original inequality here. So for example, 0 is in this interval here. So I'm going to test x equals 0. So then right here, that means I'm saying 4 times 0 is less than 12 minus 0 squared. 4 times 0, of course, is 0, and 12 minus 0 squared is still 12. 0 is less than 12, which is completely true. Therefore, the interval from negative 6 to 2 is part of my solution set. All of the numbers in here, no matter which one you would have picked, would have given you a similar result. Okay, next, let's test the interval from negative infinity to negative 6. I would do so by substituting a negative 7. Let's see if I can actually squeeze that in here. If I plug in, I'm going to do it down here. If I plug in negative 7, 4 times negative 7 is less than 12 minus negative 7 squared. I have negative 28 is less than, this is going to be 12 minus 49. Don't forget the squared gets rid of that negative. So I get negative 28 is less than 12 minus 49 is going to be negative 37, which of course this is false. Negative 28 is not less than negative 37 because you're on the negative side. Okay, so that means this is a false right here, right? Remember, I was doing it down here because I ran out of space. That's this right here. So I will not be using this interval. Okay, and then for the last bit here, I'll test 3. So 4 times 3 less than 12 minus 3 squared. That's 12 is less than 12 minus 9. 12 is less than 3, which is false also. Okay, so let's sum it all up. The only true that I got was from this interval. So my solution set is where x is an element of the interval from -6 to 2. Notice no brackets because no equal sign. So we find the breakpoints. Those breakpoints give me sections. I test each section, right? That's the advanced technique for solving most of your nonlinear inequalities. Okay, so what about a rational one, right? Still works the same way. I'm going to find those breakpoints, right? So breakpoints. I do so by setting it equal to 0. And I'm going to factor these. X squared minus 6x plus 9 factors into x minus 3 times x minus 3. So I'll just put x minus 3 squared. Or if it helps, you can, I'll just go ahead and factor it out. That's fine. I'll show the steps there. And then this bottom piece right here also factors. If it didn't, you could always use the quadratic formula. But this one factors, let's see, 2x and x. They're each going to have a 1. It's got to be -3. So let's put a negative on each one because -1 times -1 is 1. Yeah. So that gives me, yeah. So it factors like this. Notice nothing will reduce. Okay. But I can read the breakpoints off of this because it's anywhere that any one of these is going to equal to 0 or undefined. So I get equal to 0 when x is equal to 3. I get undefined when x is equal to 1 or when x is equal to 1/2. Okay, now these are not necessarily solutions. Okay, and it is worth noting that x equals 3 is the only one that is making this thing equal to 0. All right, that's the only equal 0 point. These other two right here are making it equal to undefined. Let's write it out. I'm sorry, I shouldn't use my fingers to erase that. It's very, very important that you remember those two distinctions. Since I have the equal sign here in the actual original problem, I can still use any of the breakpoints that give the equal to 0, like equal 0. So x equals 3 is actually one of the solutions. I've already found it. It's one of many. But the 1 and the 1/2, they're still breaking points, but it's equal to undefined because those are division by 0. So those will not be solutions ever. You cannot use those as solutions. Okay, so now that I have the breaking points there, I'm going to put my axis on here. And instead of numbering it this time, I'm just going to put the numbers up here in order. Okay, so then of course 1/2 would come first. And then 1. And then 3. So those are my breaking points. I'm going to make the little intervals here. Right? Here's my little sections. And then I'll pick a number from each section and test it, right? This section right here is -infinity up to 1/2. And 0 happens to be in there. So test x equals 0. Okay, so I plug that into the original. That's going to be 0 squared minus 6 times 0 plus 9 over 2 times 0 squared minus 3 times 0 plus 1 greater than or equal to 0. So of course 0, 0, 0, 0. I end up with 9 over 1, which is 9 is greater than or equal to 0, which is absolutely true. Okay, another little thing, if you remember, I would have shown you a pattern that you can do these things with. If you look at the exponent for each one of these things, and again, this is where this x minus 3 Remember, I didn't have to write it this way. I could have written it as a squared. Anytime you cross over one of these boundaries, one of these breakpoints, if the exponent is odd, it's going to switch the value. So 1/2 has a 1 power on the factor. This next one's going to be false. It will switch. 1 also has a 1 power. So when you go across this, it's going to switch again. This is going to be true. However, the 3, technically it was a repeated root. It has a squared. So right here, when you go across this boundary, it will stay. It won't switch. So this section should also be true. Now, of course, we're going to go through and check this, but I wanted you to notice that you can actually predict these patterns. You can also come back here and notice the same thing, right? We knew this middle one was true because I plugged in 0. Then if I go across either one of these boundaries, notice both of these were to the 1 power. It should change, right? So true changed to false, true changed to false. We could have predicted it that way on that one as well. Okay, so in each of these, let's do some predictions here. For example, between 1 and 3, I could test x equals 2, right? Test x equals 2. If I plug in 2 right here, right? 2 squared is 4. Minus 6 times 2 is minus 12. So 4 minus 12 plus 9 is 1. Okay? And if I plug in 2 here, 2 times 2 is 8. Minus 3 times 2 is minus 6. 8 minus 6 is 2, plus 1 is 3. 1/3 is greater than or equal to 0. Notice, completely true. Right? 100% true on that one. If I test something bigger than 3, let's say 10. 10's easy to test because it has a nice round number of pieces to it, right? So let's see. If I do 10 squared is 100, minus 60 is 40, plus 9 is 49. Right? Then this would be 200 minus 30 plus 1. That'd be 171. Greater than or equal to 0, which, as you can see, is also true because it's a number bigger than 0. It is positive, it's bigger than 0. Okay, and if you want to test something in between 1/2 and 1, I would say, what's something easy to test? Well, this is 0.5, right? So what's something easy to square and such? Woo! Not so nice on this one. Let's do 0.6, I guess. 0.6 is the value in between there. Okay. So then, let's see. I'll use the factored version right here. That might be easier. 0.6 minus 3 is negative 2.4 squared over 2 times 0.6 is 1.2 minus 1 is going to be just 0.2, 0.2. And then 0.6 minus 1 is negative 0.4. Okay, now if I do that calculation, I want you to notice what's happening here. I'm not even going to bother doing the multiplications because I can see the numerator is going to be positive because of the squared. The denominator is a positive times a negative, which is negative. And they're trying to claim that this is greater than or equal to 0. Okay? This is 100% false because you're going to get a division that ends up being negative, which is a negative number, right? Which is not greater than 0, which is absolutely false. Okay, so you can go through testing each one, or you can do the pattern. Finalize this with a solution set here. Solution set. X is an element of, we have negative infinity to 1/2. Notice I am not including the 1/2. It's an undefined break number. Union with I have everything from 1 to 3 is this interval. Okay? And then union with 3 to infinity. Now take a step back. 3 was an equal 0, and remember we said we can have the equals. It was in the original problem. So instead of parentheses here, this should be a bracket, and this should be a bracket, right? Lo and behold, I can actually merge these two intervals. So my solution set, x is an element of negative infinity to 1/2, union with 1 to infinity. Those two sections can merge because of the equals. If that equals had not been there, I would have left them as parentheses, and you would have just left it separate. But because of the brackets here, I can actually merge those into one interval. They're connected. They include every value. Okay? So I hope this has helped you get an idea of all of the different topics that can be on this first test, all of the solving of equations and inequalities that we've run into at this point. Remember, do not memorize any particular problems. You should practice the methods. Find other problems that are similar to these and even maybe a little bit different, and practice the skills, practice the methods. Memorize methods, not individual problems. It will work against you if you're memorizing individual problems. Okay? I hope you have a good time with the examination.